Horst is the project manager, the project coordinator for OBELICS. Horst is responsible for the global research program at AVL within the Instrumentation and Test Systems division. Horst studied electrical and automation engineering at the Technical University of Graz and worked for 15 years in the field of test design and optimization of electronic controls. He was responsible for the software development of the product Cameo. Horst has held the position of Global Research Manager in the Central Research Department at AVL since 2010, and he has established and managed several research projects in the field of electrified and automated driving. Horst, the floor is yours.
Thank you very much, Andy, for the kind introduction. I would like to give you now a short overview about OBELICS, and the name OBELICS, I think it's appropriate because it's the successor project of Asterix, which we already did in the past with similar partners and similar topics actually to bring that to the next level. It's an abbreviation, and I want to also only look at the word optimization, because optimization is actually trying to find the best solution. And in reality, the optimal solution is always a trade-off between different topics. This is, as Matthias has explained it just before, that's actually what we try to support with this project. Our vision in blue that you can read on the slide is that we wanted to create here a comprehensive framework that supports the design and the development and the testing of the optimal and the advanced e-powertrains and electric vehicles. For that, we have used more below the next blue text, the model-based testing methods, and also scalable and easy to parameterize real-time models. The objective in green actually is to reduce the development efforts, as always, in this case by 40%, and to improve the efficiency of the modern e-drivetrain by 20%. And the third objective was the increase of the safety by a factor of 10. Let's look how we did that and who did that. Our project started in October 2017. We have now the project duration of 38 months because of the pandemic crisis. We increased a little bit the duration. We have 19 partners from 9 different countries, and you can read them here, from car manufacturers like Renault Truck, Volvo Truck, CRF, Fiat, and Ford Otosan, then to the suppliers, Tier 1 and software hardware supplier, Bosch, Valeo, AVL in Graz and in Regensburg, Siemens in Brussels and also in France. We have our project management support with Uniresearch, and we have a lot of research organization, which you can read here, which had a great influence also on the results that we have created within this project. Our approach is actually that we started from the V-cycle, the well-known V-cycle, which you all know in different forms, I would say. And we actually did or entered here additional small iterations on every level. On the left-hand side, you see model-based testing, for instance, which needs to be introduced in this form, actually, or bring it to the next level, I would say. We have also scalable models that we want to use throughout the entire V-cycle, and the testing methods on the right side of the vehicle shall also be improved of the V-cycle. That means we want to shift that a little bit to the left, and that is what we call also front loading, and with that we want to reduce the efforts. So the gray V in the background is actually the starting point, and the end point is minus 40%, and with improved efficiency and reliability and safety as well. The topics that we covered in the project are also reflected in the work packages. So we have use cases. I will tell you more about that soon. We have safety assessment methods in the work package 5, and those set the boundaries and the requirements for our work in the project. The technical topics in green here, work package 2, 3, and 4, are real-time models, scalability of real-time models, the model integration into a system, and also the functional testing. At the end, in gray, you see the demonstration and evaluation, and also to check whether we have reached our objective. And finally, the standardization, dissemination, and exploitation. We have 17 use cases within this project. That's a tremendous amount, actually. We have clustered them into 4 clusters, or we can also say engineering categories to that. The first one is the Edrive concept design. We have the next, the e-vehicle system integration and optimization. Then we have battery design and testing. And finally, we have e-motor control and inverter design and testing. Let's look a little bit closer into these 4 categories. If you look at the Edrive concepts, you see also the partners that worked here in the different use cases, and also the scope that they had in this table on the left. So the powertrain, topologies, optimizing them, e-motor design, for instance, auxiliaries, thermal management, a lot of different aspects that influence actually the performance and the reliability and also the driving range of electric vehicles. And you see also the cluster main purpose. So it is at the end, it's a faster workflow for the new electrified powertrain concept supported through this framework. And on the right-hand side, you see a sketch, actually, that tries to more or less display what we are doing, how this workflow looks like, and what items we are using here to make this workflow possible. And associated with this cluster are also specific targets like the efficiency improvement by 20%. There's also a reduction in development efforts that we want to get out of this use case cluster. Now, if you look to the second cluster, this goes more in detail. It's already the system integration and the optimization. We have now here 4 different use cases, or even 5 at the beginning, but we merged 2 of the use cases, or we brought them together because they were so close to each other on the top of this page, and you can read through the details here. I don't want to go into that too much, but you see on the right-hand side the sketch actually of a system view, so you can't see it in details. That is why, or this is why, because there are so many details actually to optimize, and this optimization can only take place if you know all the aspects that influence actually the performance or the efficiency of your vehicle in one model. And the cluster main purpose is actually to support this workflow and also the integration of these models, and to get out the optimized solution for your specific purpose. The third cluster is battery design and testing. You see 4 use cases here. And you see also a few pictures on the right which indicate what we are working on, actually. You're seeing here, for instance, this mechanical assessment on the right side on this blade, on this mechanical blade, actually, that tries actually to excitate the mechanical load in the testing area. You see also that the battery tester was equipped with sensors actually that measured the movement of the parts within the vehicle. We have also done here some testing technologies for the battery, and the cluster main purpose is to increase the safety of the electrical mechanical components of the battery, and to provide a very high level of safety due to this probabilistic FMEA, which you will hear later on in the booth number 2, I think, or second one from OBELICS. You will see it later. The fourth use case cluster is Emode and Inverter design especially. We have 5 use cases here. The cluster main purpose here is to explore different levels for the Emode and the inverter and also the control of those components. We have a lot of different models here that go into depths. We have also some hardware-related development, FPGA controllers that simulate that fast movement and that fast signals that we have within the inverters and the E-motors in order to have a good environment to test and to develop those components. Here I just want to give you an impression about the technical content of the work packages. So if you look at these real-time models and the scalability, then you see that we moved, or that we have for all 3 components in the e-powertrain, the battery, the e-machine and the inverter, very detailed models. For instance, for the battery, we have electrochemical models. We go very much into depth, but we use them throughout the entire development cycle. That means we have to provide here also scalability. For the e-machine, you see also a few models for different e-motors and that we have used within the project. And for the inverter, you see the high frequency domain or the high frequency level actually switching losses, switching transition, conduction losses actually, so that we can optimize all these components. The model integration is work package 3. If you put everything together, you have to think about, okay, how do I put that together? Because often it's not only one company or one partner that is providing these components, they are different ones. That means you have to think about what are the right interfaces and how can you use that. You will hear that later, I think, also in the HIFI-ELEMENTS presentation. If we have put that together, we want to optimize it and we want to get out the best trade-offs actually. And that is what this work package about. The work package 4 is about testing methods. So how do we test actually batteries? What is the best methods? Do we need realistic high frequency testing? Does that have a big influence to the battery lifetime, to the battery performance? And we have to simulate that, and we use therefore FPGA-based controller platform to have that available also in the lab and in the testing lab. And we have also applied this multi-sign-based EIS testing signals actually to find a very fast way to scan the battery very quickly and to get an immediate response how the battery looks like. The same is true for the inverter testing methods. We have here several methods how to test inverters in physical form and also together with models, for instance, for the e-motor. There's a lot of sensors that are involved actually in measuring the right signals in order to do this testing and to do the further optimization. Work package 5 is about safety and reliability. You will hear that on the booth, so I go not too much into details, but this probabilistic FMEA assessment is a very good means to assess the safety of the electric components. You see some pictures here on the top right, how this all fits together and how this influences the safety, overall safety. And you see some pictures on the bottom. This is the dynamic battery excitation that we had. This is related also to the use case cluster 3 that I showed before, and some signals which compare actually the real signals that we have measured on the road and the one which are actually given from the standard, how this should be measured, and you will hear later some comparison and how this looks like. Now, at the end, for us also the question in work package 6 is how do we demonstrate that, what we have reached within the project, and how do we measure it? So all the objectives that we have here, the efficiency improvement, the safety improvement, and the effort reduction, how do we measure that? And you just see here a few influence factor. This is not the final results. We are still working on the final evaluation of that. I would have to show this today, but it was not possible due to the shift that we have a little bit in the project. But out of this influencing factor, we can measure what is the influence of every use case and every method that we apply within the project. And we will share, of course, the results with you if we finally have them. I think you will hear a little bit in the booths as well. The final topic that I would like to mention here is the standardization activity, where we were working together with HIFI-ELEMENTS actually on the model standardization. So you see some approaches that we have developed within OBELICS, for instance, this system identification card here on the left, or the picture on the right, the left upper one, and the channels, for instance, and the input and output definitions. We compared that. We have done a lot of comparison, and we find out at the end that we are very similar with the approaches. You will hear more of that at the HIFI-ELEMENTS presentation, I think. But this was a very good interaction that we had within the project phase, and that we are continuing until the end of the project. This was it from my side. Here the contact details from myself as a coordinator, and Uniresearch, Wilhelm van Dorp as a project manager, as a very great support in this project. And you find also the OBELICS homepage and webpage where you can find further information. Thank you for your attention.
Are you going to? Okay, thank you, Horst. We're a bit ahead of time, so we have time for questions. I'll ask in a moment for questions from the audience. If you have questions, type them into the chat. I have one for the moment. Matthias showed us the VW approach, which, if I understood it, was completely new. Mm-hmm. And on the other side, he had the BMW approach, which, if I understood it, was to take a one-size-fits-all approach and stick with old technology, and you in the same skin. What is OBELICS? Is it something new, or is it warming up something that's already been done?
Mm-hmm. Okay, that's a good question, Andy. In this context, I would say we do not prefer a specific solution at the beginning with OBELICS. We are rather open to any solution. That means with OBELICS, we provide the framework where you can simulate and test upfront the different solutions, the one from Volkswagen, the one from BMW, and compare them with each other. And also there are many aspects, actually, there are many questions. Matthias showed us, okay, what is the right sizing of the components? What is the right overall approach? In general, is it a battery electric vehicle? It might be even a hybrid electric vehicle. So the platform and the methods that we have provided are still open for any solution. That means with the work that we did here, we provided actually the basis for the decision and for the optimization. And of course, you have to define for your decision, what are my criteria? Yeah? What do I want to serve? What is the end goal of my specific solution, actually? And everybody has to define it by themselves.
But what I understood from Marina as well, she said there's an urgent need for new methodology, mm-hmm. which kind of equates to the VW approach. They do everything new. What is new? What was not possible before this project that is possible now?
Mm-hmm. Okay, the main contribution that we made here is the detail of the modeling, actually, the accuracy of the modeling that we can provide, actually.
That wasn't possible before.
That wasn't possible before. We have so much in-depth modeling, for instance, for the battery, the chemical properties, you can put that in the same simulation actually as the entire simulation. It's always a question of computing power at the end also. So the computing power that we have today is much higher than we had a few years ago. That means we can simulate much more together at the same time, and we can put that also in our decision if we want to. I do not say now that the chemical factors are decided with at the same time with, for instance, the vehicle size. Yeah, that might not be the question, but there are many questions actually. What is if I change actually the battery? If I put a different platform? If I make a bigger battery? If I use other battery cells? What is the influence actually, the overall influence?
Okay, so you're saying that the idea of simulation is not new, but the abilities you have, the models that you're using, they are different. They are new now. And the battery itself is challenging you because it has chemical processes that you didn't need to model before. Is that also what you're saying?
This is also true. The battery is one of the important key, I would say, for the electrification, because it's the most expensive and the most expensive part actually, and it consumes a lot of resources also in the production of the materials. That means,
as we saw from Matthias, yeah.
Right. So as soon as we have a battery that has 1 kilogram and 200 kilowatt hours, everything is solved.
Next year.
So the question is, how do we go further? Actually, how do we take the optimal decision? How do we shrink the battery? How do we make it more performant? How big is the battery that we need actually for our use cases? Not every use case. So if you drive to work on a daily basis, it's different if you or if you go a long haul trip every day because you want to sell your goods or whatever.
So a lot of this is being driven by the battery because that is the thing that's new.
It is driven by the battery, but not only. This is just one big influence factor. Okay. And of course, also the e-motors are developing further. Yeah, so the e-motors are getting smaller, they are getting more performant. The inverters actually are going to higher frequencies. We have now switching frequencies up to 20 kilohertz, as you see, for instance. We have this modern silicon carbide technologies. We also have to model that kind of wide bandgap.
Well, here's a question from a dinosaur. I remember 1984. You won't. In my day, you had a combustion engine and it burnt things.
Yeah.
But it burnt them fairly quickly. It was basically a slow explosion. So you measured it in crank angle, and you tried to measure crank angle. You tried to combine crank angle data with time-based data. Are you doing that again now with chemical processes and your viruses that fire at kill? Do you have the same kind of problem? You have different bases for the simulation?
It is true that we have that. I would. What immediately comes into my mind is actually in a hybrid solution. So if you have the combustion engine together with the battery and with the battery powertrain and the electric powertrain, because you can actually, for instance, move very important cycles of the combustion engine. You can remove them, you can avoid them, and replace it by the torque that you get out of the electric machine. This was just one example. I think there are many ones.
And we'll
also
talk about
in the
it in
pure
a
electric vehicles, and let a little bit space also for the other experts to explore on that.
Well, Horst, thank you very much for your contribution. Oh, we have another question. Wait. I'll read it. Thank you. Is it the top one? Oh, here we go. We have a question from Alain Buscarayol. I hope I've pronounced that correctly. When you use different levels of models for the same component, do you use different software?
Yes, and I think it's dependent actually, because the software that is being used is always at the beginning decided by the one who make this model, who built the model actually. So one is using MATLAB actually to build the model. Other people are using more the commercially available tools like the Cruise or the AMSIM or other tools actually which are on the market. And they built it just with their software. And then we have created and defined this standardized interface. It's called FMI and FMU. This stands, I don't know for what.
That's what Alan is probably saying. He's probably saying the answer is yes, it's different software, but don't worry, you can combine it.
You can combine it. There are platforms actually where you combine everything. That means you can put every component from different partners into one simulation, put them together.
Okay.
You have to define the interfaces up front, otherwise you cannot combine them.
But they're standardized,
we try to standardize. They are not standardized until yet, but we have made
working on it.
We have made a huge step forward on this, and therefore I think that's the answer. It's different software, and we combined it in one platform.
We've got time for one more question, and it's on here. If a developer or manufacturer wants to use the innovation from OBELICS in their process, how do they do it? Will there be one OBELICS package? Will the simulation or these tools be commercially available?
Yes. The output of OBELICS actually will be available, will be integrated into the product. As I mentioned before, we have the software suppliers, we have the hardware suppliers, mentioned also on the second page, more or less. They will integrate this capability into the products, so as AVL also does, of course, and this will be available publicly in that form, in the commercial form. There are also the institutes, the universities involved. They have also a lot of insights, and they are also there to spread the results further, and they have already done. There are many publications outside, and if it comes into details, then you have to approach the partners, of course.
There you go. Well, Horst, thank you very much for the overview of OBELICS. Thank you.
Thank you.